Hello all, welcome to the channel. Today let us discuss about the chapter 1 of physical science chemistry. In textbook it will be chapter 2, but for chemistry part this is the chapter 1 of grade 10th state board syllabus. Now before we talk about chemical equations and balancing and all the various topics of this chapter, we need to know how many changes are there and what type of changes do we have in the nature. So changes can be mainly physical changes and chemical changes. We need to know the basic difference between physical and chemical changes. Before that, everything that happens around us, we can observe the changes like the digestion of the food, burning of crackers, respiration, that the air that you breathe, all these come under changes. Now among these changes, which change is physical or which change is chemical can be categorized based on some features. Physical changes mainly happen in the physical forms like the physical state or color or size, etc. So when you observe the change in the physical properties like state, color and size, such changes are called physical changes. Whereas if you observe the change in the chemical composition, what do you mean by chemical composition? Chemical composition is nothing but the formula of the compound. Such changes are called chemical changes. And when a physical change happens, we can reverse the change in most of the cases. But in a chemical change, the change can be reversible, we can reverse, or we cannot reverse. It can be permanent also. Most of the times the chemical change will be permanent, but in very few cases, in very few conditions, you can attain the products again to reactants. The reaction can be reversible sometimes. Okay, and these physical changes or the substances that are formed by physical change, we can separate them by physical methods. The substances formed by the physical change, we can separate them by physical methods. For example, if you have mixtures like sand and water, soil and water, salt and water, all these we can separate by using the physical methods. Whereas if you look at the compounds like water or carbon dioxide or hydrogen peroxide, all these compounds that are formed by the chemical change, we cannot separate them. They cannot be separated by using the physical methods. We cannot separate the chemical compounds simply by physical methods. These are the basic differences between physical and chemical changes. Let's move on to the next part of the chapter, that is the activities. Various chemical equations are explained in terms of activities. So the first activity is we take calcium oxide. Calcium oxide formula is CaO and its normal or common name is the quicklime. CaO is called quicklime or calcium oxide. Now when you add this calcium oxide to a beaker of water, so if you have taken the beaker water and to this you added some calcium oxide. Calcium oxide is a powder which is white in color. So as soon as you add this calcium oxide white powder to the water, then you observe the whole liquid gets turned into white color solution. Now this is your calcium oxide solution. Now the reaction that happens here is calcium oxide reacting with water gives rise to calcium hydroxide or slaked lime. This is slaked lime and this is quicklime. Now here the chemical reaction is happening. How can you say that? Because here the formula was CaO, now it turned into CaOH twice. Now the chemical composition has completely changed. And what other change you observe? What other change we observe is, we observe the beaker getting hot. When you touch the beaker, surface of the beaker becomes hot. That means this reaction is releasing energy outside, energy is released outside, which is nothing but the exothermic reaction. The reactions which release energy outside are called exothermic. The solution that is formed here, calcium hydroxide, is a basic solution. The nature of the solution is basic. That we can understand by placing a red litmus paper in the calcium hydroxide solution. Now the solution, whatever part is dipped in the solution, the paper that is dipped in the solution turns into blue color. This reveals the nature of the solution, that is basic nature. Let us move on to the activity 2. Here in the second activity, what we consider is two different salts, that is Na2SO4, which is sodium sulfate, and BaCl2, that is barium chloride. These are the two different ionic compounds which are both white solids, white powders. These are two white color compounds. Now, in order to perform the chemical reaction or activity, we have to mix these salts in water and form aqueous solutions. Now we get sodium sulfate aqueous solution, which is Na2SO4 aqueous solution, and BaCl2 aqueous solution. Both become colorless because they are completely dissolved in the water. So we take sodium sulfate in one beaker, which is a clear solution, and to this sodium sulfate we start adding barium chloride solution through another beaker. Now as soon as the barium chloride solution mixes with the sodium sulfate, we observe a white color precipitate formation. Here I shall use light pink color to indicate the white solution. We observe a white color precipitate forming immediately when the barium chloride reacts with sodium sulfate. Now what is the reaction that is happening in between these two is sodium sulfate reacts with the barium chloride to give sodium chloride plus barium sulfate solution. Here sodium sulfate has Na plus and SO4 2- ions. Here barium chloride has Bas2 plus and Cl- ions. Now these two get exchanged with each other. Sodium goes with chlorine, barium goes with sulfate. Now that results in the formation of sodium chloride, which is dissolvable salt, and barium sulfate. Now the question is, barium sulfate, is it soluble in water or not? No. It forms a PPT. It forms a white color PPT, which we can see clearly in the solution. This is the chemical reaction happening between sodium sulfate, barium chloride to give sodium chloride and barium sulfate. Now let us look at the activity 3, where we talk about the reaction between zinc granules with hydrochloric acid. Zinc granules, in the sense we take small pieces of zinc in order to perform the reaction better. So there is a conical flask this way. We take a conical flask in which we take some amount of acid. We take hydrochloric acid, which is in dilute form, and to this we add zinc granules, which are small pieces of zinc, some amount. Then what we observe is slowly some fumes coming onto the top of the conical flask. I am showing the gas in the form of dots. So this gas, colorless gas, starts evolving from the conical flask to the top. We can cover this lid with a watch glass. We can cover the mouth of the conical flask with a lid or a watch glass, and we see the gas getting built up in some time. Okay, so some gas is getting built up in the conical flask, and after some gas gets built up, we can remove the lid and bring a burning matchstick near the mouth of the conical flask. Then we observe this matchstick puts off. Now while it puts off, it puts off with a pop sound. It creates some sound which is like pop. Okay, this indicates the released gas is nothing but the hydrogen gas, because hydrogen gas is not a supporter of combustion. It does not support combustion. This can be proved by the burning matchstick when it puts off, when it comes in contact with the hydrogen gas. And now the product formed here is zinc chloride. So zinc reacts with hydrochloric acid dilute form and produces zinc chloride, which is the aqueous form, and hydrogen gas is released. So here hydrogen gas can be released by those metals like zinc, copper, iron, only which are more reactive than the hydrogen. Only those metals can react with hydrogen and evolve hydrogen gas when it reacts with the mineral acids. So from the above three activities, we can come to a conclusion that the chemical changes are associated with the following changes or following characteristics. What is that? The original substance, the initial substance that you take, will lose its characteristic properties compared to the final product. That means if you consider calcium oxide turning into calcium hydroxide, as we have seen in the activity 1, where the formula is completely different, that means the properties are completely different. So the initial reactants and the final product's properties are completely different with different physical states and different colors. Okay, this is the first characteristic. What is the second characteristic? The change that we observe can either emit energy or absorb energy. That means the chemical reaction can take place while it emits energy or absorbs energy. So the reaction can be either exo or endothermic forms. This is the second characteristic of a chemical change. The third characteristic is, during a chemical change, we can see sometimes the substances are soluble or insoluble. When the substances are soluble, it's completely fine. When the substances are insoluble, then you call it as precipitate. If they are soluble, you can call it as solution or aqueous state. If it is not soluble, then you call it as a precipitate. The fourth criteria or the characteristic is, gases are also can be evolved, as we have seen in the recent activity. So gas may be evolved as the product. Gas may be evolved as the one of the products. So these are the main characteristics that we see for chemical changes. Chemical equation is the short form representation of a chemical reaction or a change. For example, instead of telling that calcium oxide reacts with water to give calcium hydroxide, this is a very long statement. Instead, what do is, we either write the name of the compound like calcium oxide plus water, which give rise to calcium hydroxide. This is the word equation. This is the word equation. This is also a short form. This is also considered to be the longest representation. So instead, we give the formula of the compound, that is calcium oxide formula is CaO plus water formula is H2O, giving rise to calcium hydroxide formula is CaOH twice. This is the representation of a chemical equation, where the left side, whatever substances are there, they are called reactants because they react to give some end substances. The end substances are considered to be the products. There can be one or two reactants. So we separate the two reactants with a symbol plus, and the end products are written on the right side. Reactants are written on left side. So to indicate that the reactants are converted into products, we put an arrow between the reactants and products. So the overall representation of the reactants combining with each other to give products is nothing but the chemical equation, which is the short form representation of the chemical reaction in terms of the formulas of the compounds. Let us look at the most important part of the chapter, that is balancing of equations. Now we have studied how to write a chemical equation, but is it necessary to balance a chemical equation? Let us see. So we have a law called law of conservation of mass. That means mass can neither be created nor be destroyed, but we can convert from one form to the other. This law states that mass in an equation, if you consider the reactants converting into products, so mass before the reaction and after the reaction, mass remains the same. It is exactly the same. In such condition, in order to follow the law of conservation of mass, we need to balance the equation. What do you mean by balancing of equation? We should see if all the atoms on left side and right side are equal in number or same, then the mass is said to be equal, and that follows the law of conservation of mass. Then that is the balanced equation or stoichiometric equation. Now let us see this with an example. We have combustion of propane. Combustion of propane means we need to burn propane in the presence of oxygen. So propane formula is C3H8 plus O2. On combustion, any carbon compound on combustion gives carbon dioxide and water. Now let us see if this is a balanced equation or not. We need to check if all the atoms on either side are same or not. Here carbons are 3, hydrogens are 8, here oxygens are 2. Oxygens are 2 plus 1, 3, carbons are only 1, hydrogens are 2. So it is very evident that this is an unbalanced equation. Now we need to balance this equation. So the first step to balance is writing the formulas of each reactant and product. Now this is considered to be the unbalanced equation or the skeleton equation. Now the second thing that we need to do, second step, is we have to select a complex compound, or we can say that uncommon compound. In this reaction, oxygen and hydrogen are very common. The uncommon one is the propane, that is C3H8. Now we need to start adding coefficients instead of changing the skeleton. That means C3H8, O2, CO2 and H2O remains the same. We should not touch the skeleton, but we need to just add the coefficients on the left side. What do you mean by coefficients? They are the formula units, or how many parts of C3H8 will participate in a reaction, how many parts of O2 will participate, how many parts of CO2 is formed, and how many parts of H2O is formed. That number is nothing but the stoichiometric coefficient. That number is called the stoichiometric coefficient. Only that number we are going to multiply to the given reactant or product. We are not going to touch the skeleton. This is the major criteria that we need to remember. Then here we have 3 carbons. On the right side there is only 1. So what do? We multiply the right side carbon with 3. So we get C3H8 plus O2. Then that gives rise to 3CO2 plus H2O. This is the second step. Now what else we have? We need to look at the oxygens. Oxygens are how many on left side? There are 2. On the right side there are 3 into 2, 6 plus 1. 7 are there. So to get 7 oxygens on the left side also, what do? Now look at the hydrogens. On the left side we have 8 hydrogens. On the right side you have 2. So you can multiply this 2 with 4 to get 4H2O. Now that the hydrogens are balanced, the next step we can look at is the oxygens. So we have C3H8 plus O2 gives rise to 3 CO2 plus 4 H2O. The equation is almost balanced except for the oxygens. So on the left side you have 2 oxygens, but on the right side you need to multiply this 3 with 2. 3 into 2 will be 6 plus 4 into, here there is no number, so you take it as 1. 4 into 1 is 4. So 6 plus 4, it is 10. Then you need to multiply 5 O2. So it is 5 into 2, 10. Here the most important thing that you need to remember is whatever number is on the left side, that is applicable for both the atoms, or the every atom present in the molecule. That is, suppose if there is 1 here, that 1 should be multiplied with this 3 as well as this 8. But if the below number is there, that is applicable only for that particular element. This 3, C3 indicates that 3 is belonging only to carbon. But if at all you write 2C3H8, suppose, that means that 2 is belonging to both 3 and 8. This is the major criteria that you need to remember. So this is now the balanced equation. This is now the balanced equation where all the carbons, oxygens and hydrogens are balanced. Now this is called stoichiometric equation or balanced equation. Now this follows your law of conservation of mass. The same equation can also be written as 2C3H8 plus 10 O2 gives rise to 6 CO2 plus 8 H2O. Now this is also balanced and stoichiometric equation, but which one need to be considered? Is it the first one or the second one? If you question, then I say that only the first one is the most considered stoichiometric equation, because we need the coefficients of the balanced equation to be a simple numbers instead of large numbers. Second equation is also stoichiometric equation, but it has all heavier numbers. The reactants and products formed are in large numbers, which is against the law of conservation of mass. So we need to consider the coefficients in a simple whole number instead of large numbers. In such case, what we need to do? We have to divide all the numbers by the simpler number so that we get a simpler coefficients in a stoichiometric equation. The chemical equations that we have balanced are known as stoichiometric equations. Those equations, though they follow the law of conservation of mass, they are less informative. We can make it more informative by adding some other representations. The first one is, we can express the physical state of the reactants and products. We can express the physical state of reactants and products by adding some symbols. Suppose if you look at iron oxide Fe2O3, iron oxide Fe2O3, this is a solid. We represent the symbol small s at the right side corner, this way. When it reacts with aluminium metal is also a solid. We represent it with the symbol small s. Now we separate the reactants and products by an arrow. This delta indicates the heating process. We need to heat the iron oxide and aluminium. After mixing with each other, we need to start heating the reaction. Then we get iron solid again, which is represented as small s, plus the other product is aluminium oxide, that is Al2O3, which is again a solid. So this way, for solids we write small s, for liquids we write small l, for gases we write small g, and if you mix any salt or solid substance with the water, then you call it aqueous solution and you write it as AQ. These are the various representations to indicate the physical state of a substance, and make it more informative. Then the second feature that we are going to add is about the heat changes. We express the heat changes. Suppose if the reaction is followed by the emission of heat. Suppose you burn carbon with oxygen to give carbon dioxide. Here a lot of energy is released. In such case, what do? Is we add Q on the right side, which indicates exothermic reaction or evolution of heat. Suppose if the reaction is absorbing the heat, N2 plus O2 give rise to NO minus Q. That means the reaction is endothermic reaction. These are all added after the balancing of equation, that is N2 plus O2 give rise to 2NO. Now this is the balanced equation. And also if you can write the physical state, then this is solid, gas, and CO2 is also a gas. N2 is a gas, O2 is a gas, and NO is also a gas. This way we add heat changes to the equation. Now the third one is we express the gas evolved with some symbol. Suppose if you take zinc and H2SO4. Zinc is a solid, H2SO4 is aqueous solution because we take dilute form. Then that results in zinc sulfate, that is also an aqueous form with evolution of H2 gas. So whenever we have any gaseous products in the reaction, we use the upward arrow along with the G symbol. This is another expression for making the chemical equation more informative. And the last one is about the precipitate that is formed in a reaction. Suppose AgNO3 aqueous form is treated with sodium chloride aqueous form. Because these are all salts, we need to take it in solution form for the reaction to occur. Then we get AgCl plus NaNO3. NaNO3 is soluble in water, we write it aqueous, but AgCl is not soluble, it is a white solid precipitate. So we indicate the precipitate by a downward arrow. For a gas we put upward arrow, for a precipitate we put downward arrow. By adding all the four features, we can make the chemical equation more informative. The next and the most important part of the chemical equation chapter is interpreting the balanced chemical equation. That means what all information we can get from a balanced or a stoichiometric equation. For example, we consider the equation that is 2Na solid reacts with 2H2O liquid, which give rise to 2NaOH aqueous solution plus H2 gas. So we added all the informations in the chemical equation. Now from this balanced equation, what we can interpret is we can know what are the reactants and what are the products of a reaction. Then we can know the ratio of the reactants and products, 2:2 give rise to 2:1. Then we can know the unified masses. Since we write all the molecular masses in terms of unified mass, we can know the relative masses of all the reactants and products. We can express them in the grams units instead of unified mass. Then we can know how much gas is evolved in a reaction and how much volumes they occupy. So we can use all the mass-mass relationship, mass-volume relationship, mass volume and number of particles Avogadro relationship, as well as volume relationship to do all kind of calculations. Let us perform one such calculation and understand what all we can interpret from a balanced equation. So sodium unified mass is 23. So there are two units of sodium. So it is 2 into 23 unified mass. Then we have H2 is an compound. Here sodium was an element, but H2O is an compound. So 2 into 1 hydrogen is 2 into 1 equal to 2 unified mass. Then you have 1 into 1 oxygen, that is 1 into 16 equal to 16 unified mass. This is 18U for 1 H2O unit, but we have 2 H2O units, so it will be 2 into 18, that is equal to 36 unified mass. Then we have sodium hydroxide, another compound. So one sodium is 23 unified mass, 1 oxygen is 16 unified mass, then you have 1 hydrogen, 1 unified mass. Overall it is 40 unified mass. But we have 2 units of sodium hydroxide, so 2 into 40 will be 80 unified mass. And for hydrogen, if you consider, hydrogen is 1 unified mass, but we have 2. So 1 into 2 you get 2 unified mass. Let us check if the equation is balanced or not. Left side you have 46U plus 36U. 46U plus 36U will be 82U. Then left side also you have 80 plus U, 80 plus 2, that is 82U. So left side and right side masses are equal. So this is a balanced equation which follows law of conservation of mass. And you can write the same masses in terms of grams as well. So 46U will be equal to 46 grams, 36U will be 36 grams, this is 80 grams, and this is 2 grams. We can use this grams representation for the calculation. So here's the question. Calculate the volume, mass, number of particles of hydrogen gas that is evolved when 230 grams of sodium reacts with excess water at STP. So according to stoichiometric equation above, this equation, 46 grams of sodium is reacting with water to give 2 grams of hydrogen. We are only concerned with sodium and water, sodium and hydrogen, because only those two are related in the question. So 48 grams of sodium gives 2 grams of hydrogen. Then 230 grams of sodium gives how much hydrogen? We need to cross multiply. So this multiplies with this multiplies with this. So x into, we consider the unknown value as x. X into 46 equal to 2 into 230. Then x will be 2 into 230 by 46, which is equal to 10 grams of hydrogen. So earlier 46 grams of sodium was giving 2 grams of hydrogen. Now 230 grams of sodium gives 10 grams of hydrogen, because we increased sodium amount by 5 times. This is the mass of hydrogen that is formed according to the question. Now we need to find out the volume occupied by this amount of hydrogen. According to gas laws or general laws, we have 1 mole of any gas, 1 mole of gas at STP occupies 22.4 liters. 1 mole of gas, 1 gram molar mass of gas. So instead of the term mole, we use 1 molar mass of gas. Gram molar mass of gas at STP occupies 22.4 liters of volume. So 2 grams of hydrogen would occupy 22.4 liters. Then 10 grams will occupy how much? Here also again cross multiply, take the unknown value as x, then that will be 22.4 into 10 by 2. So this will be how much? 112 liters. So the evolved gas 10 grams of hydrogen will occupy 112 liters of volume. Now the same 10 grams of hydrogen, how many particles are there in it? What do you mean by particles? It can be atoms or molecules. Then 2 grams of hydrogen contains Avogadro number, that is 1 mole of H2, which contains 6.023 into 10 power 23 molecules. It will have these many molecules. Then 10 grams will contain how much? Then again cross multiply. What do you get? X equal to 6.023 into 10 power 23 into 10 by 2. That will give you how much? 3 into or 30.1 into 10 power 23, or you can round this up as or rearrange it as 3.01 into 10 power 24 molecules. So by this calculation we can understand that a balanced equation can be related with the mass-mass relation, with the mass-volume relation, with the volume-volume relation, and mass, volume and number of particles, number of molecules relation. This is about the chemical equations chapter where we covered all the important concepts.